All right, so here is the concluding part of the lecture. Let's see. So what we want to do first is to, where we're going anyway. Where we're going is to the generalization of what we've learned regarding, discrimination of outliers that we looked at in the previous part using a single variable, to the case of more realistic multivariate situations where we have not just one frequency but 2 or 3 or 4 or whatever, right? So this is going to take us from the normal univariate Gaussian to the multivariate Gaussian, and to the fact that we're going to have to pass from there to what's known as the chi-squared distribution. Okay, so this is the second part. It's much shorter than the first, so we begin by recalling that if we have a Gaussian distribution like this, that has a mean here, and it has a certain standard deviation, we would normally refer to this thing, let's say, as normal with a mean x bar and a distribution sigma, right? The standardized version of this distribution is obtained by changing the variable x to the standard x. This was x, let's say, here. So we change it to the standard x, with the standardized x is just the variable minus the mean normalized by the standard deviation, right? So here now this is, on terms of the normalized standard deviation, then this is a sigma 1 and a mean of 0, right? So we refer to this as normal 0, 1. Okay. Now imagine that you take a variable that has this distribution, the standardized normal, and you square it. Well, if you square it, there's no need for negatives. So let's see, how did I notice? So here is the PDF of, let's say, z, which is the standardized variable squared. And so that will have some sort of PDF, which for 1 degree of freedom actually looks, well, for a scalar, looks like that, right? And it has a certain CDF, that is cumulative distribution function, which is the integral of this, right? Which is maybe something like this, right? That's the CDF, this is Z, this is Z. So if you take in the CDF a cut here, let's say, right? And that height is 1 minus the type 1 error. And you read here this Z critical, right? Then what we're saying with that is that the probability that the square of the standardized variable is less than SC, the probability that is less than that is 1 minus type 1. Let's say type 1 was 0.05, so there's a 95% chance that the square is less than this, right? Now, this is equivalent to using the actual Gaussian distribution with one distinction. In the case of the Gaussian, for one variable, we are able to say that we're going to do a one-sided test. That is, we don't care to the right side, we only care about the left side because of the nature of the physical problem. That is, damage only makes the frequencies reduced, so weird things on the right side, we don't care, they're really just weird things, but not damaged. So, however, when we do the chi-squared, we are squaring the observation, and therefore it is no longer possible to discriminate between things that are on this side or on this side of the mean, right? Because we are looking, in the standard case, right, at the square of the variable. So being larger than something the square is the same thing as to say that it is there or that it is here. So in the chi-square distribution, we can no longer do what we call a one-sided test. We can no longer say, okay, 5% probability of being on one side of the Gaussian. We can only say some percent distribution of being on either side of some limit. Now, that would not, so if we do it like this, and we say type 1 here, what we would be implying is that this would be type 1 over 2, and this would be type 1 over 2. So at this point, you might be thinking, or you should be thinking, why do I want to do that? I already have the problem solved with the Gaussian. I don't need to go to this chi-square distribution, which I guess I haven't labeled it, right? I just said z is equal to x squared, and the PDF of that looks like that, and the CDF looks like that, and this is known as the chi-square distribution. So what we say is that the distribution of the square of a normalized Gaussian is a chi-squared with 1 degree of freedom, when we're talking about the scalar case. I repeat, I have a Gaussian, I have a standardized Gaussian, obtained by subtracting the mean and dividing by the standard deviation. The collection of numbers that have this distribution, if they are all squared, they have a different distribution. That different distribution have a PDF that looks like this, and that distribution is called chi-squared. Okay? The chi-square distribution, as you can see, it's intimately connected to the standardized Gaussian, because we just took the standardized Gaussian and squared it. And look at the PDF again. So, since it's systematically related, we suspect that anything that we can see here, we can also see here. And that is true, except for the fact that because this distribution deals with the square of the variables, we can no longer look at just one side extremes, we have to look at both sides. That is not a nice thing, but the price that we pay is very small when we compare it to the benefits, which are going to be evident when we go now to the multivariate case of using the chi-square distribution. So, in essence, if instead of the Gaussian we wanted to use the chi-square to decide against, what is not a usual observation, we would simply go and do this in MATLAB. We would say z is chi squared inverse, right? Chi squared inverse, parentheses, 1 minus type 1, comma, 1. So that would give us this number, Sz. And then we would say that if z is greater than Zz, we announce damage. Right? As I say, for the single variable, this doesn't make sense, because that would mean that we would announce damage when we get things on this side, which is okay, but also when we get things on this side, which is not okay. Right? But at least mechanically, I'm trying to get the point across, right? How we go from the Gaussian to the standardized Gaussian to the square, which is this, to the CDF, to the criteria. Now, sometimes, maybe this is clear to you, I don't know, but sometimes if you don't deal with probability much, these things can be very confusing. So looking at it in terms of experiments in your head can be useful. So imagine that you have x, and that x was actually A, B, C, D, E, F, G, etc., right? So these are a bunch of numbers that were observed. Then from those numbers you can get the mean, right? No problem. and from those numbers you could get the standard deviation. No problem, right? Now, you could then get the standardized variable by taking every one of these numbers and calling this A minus X bar divided by sigma, right? And then this one would be B minus X bar divided by sigma. And you could do that all the way, right? This one would be the standardized thing that has a mean equal to 0 and a standard deviation that is equal to 1. Okay? So notice this is just an experiment. These are the frequencies. Maybe you've read the frequencies many days. So this is the distribution that if you assume Gaussian and did it normal way, that would be it. That was the previous lecture. And now we're going towards the chi-squared. So first we get the standardized version, X bar 0 and 0. Then we define Z by simply taking A minus X bar over sigma squared, B minus X bar over sigma squared, all the way like this, right? And it turns out that this distribution is chi-squared with what is known 1 degree of freedom, okay? The thing about degree of freedom doesn't mean degree of freedom like in a structure, but it's just the standard terminology that is used to refer to the fact that this one is scalar case. So this is the chi-square distribution. Now the chi-square distribution is just another distribution. And it turns out that the chi-square distribution is well understood, everything is clear. And so you can compute for that what are critical values. And so as I showed before, you could then say, okay, what is the critical value of Z? It would be the chi-squared inverse. I want to get it at 1 minus the type 1 error, right? And since I only have 1 degree of freedom in this case, MATLAB would ask me that, and I would get ZZ. Tomorrow, when I am doing some test and I get my frequency, right? So tomorrow I have an X of tomorrow, right? Just one test. So I have an X. What do I do with that X? I take that X of tomorrow, I subtract the mean from the reference data, I divide it by the standard deviation of the reference data, and I get my Z. Actually, no, I don't get my Z. I square it, and I get my Z. So now that I have my Z, I compare my Z with ZZ, right? And if Z is greater than ZZ, I say damage. Okay? And that's equivalent to having done a two-sided test on the Gaussian. All right. As I said, which is not great, the Gaussian would be better. And in fact, if we had to use, if all we had was one frequency, then there is no point in doing any of this. Just do the frequency direct, just use the Gaussian, right? But now we realize that most instances we are able to identify more than one frequency from the data. So why should we throw it away? Right? You could say, well, okay, if I have more than one frequency, maybe I'll just do independent tests, right? I'll just apply my Gaussian stuff one at a time. And you'd get reasonable stuff with that, right? But you will not get the optimal possibility from the point of view that you have to throw away the correlation between the frequencies. Okay, so let's now say that we have a vector, and so we want to go to the multivariate Gaussian. So now our X is a vector of x1, x2, etc., xk. And those are In our application, probably frequency is frequency 1, frequency 2, frequency k, right? So what is the form of the probability density function of the multivariate Gaussian? I keep losing the marker, one of the markers. Give me a second, see if I can spot it. Okay, here it is. Okay, so the multivariate Gaussian has a PDF which is given by, or at least I like to write it like this, a certain constant times e to the minus 0.5, a function that is called the Mahalanobis distance that depends on the vector x, where the Mahalanobis distance of the vector x is x minus the mean of the vector x multiplied by the inverse of the covariance of the vector x, this is transpose, times the vector x minus the mean of the vector x. That's the Mahalanobis distance, and Mahalanobis was a statistician from India from recent times. You might want to check him out in Google, learn a little bit about the man. And so Mahalanobis, right? So the Mahalanobis distance m is this, and the constant alpha is 1 divided by the square root of 2 pi raised to the k times the determinant of the covariance. That double line, which normally stands for absolute value when it's a matrix, we mean the determinant. And what else? Something I think I should have mentioned that I didn't. Let me think. No. So that's the constant alpha. Of course, this distribution, this multivariate distribution, works perfectly well also in the case of the, oh yeah, I knew what it was. The covariance is the expectation of x minus x mean multiplied times x minus the mean of x transpose. So that's the definition of the covariance. In the case of a single variable, k is equal to 1, the covariance is just the variance, which is the square of the standard deviation, and x is just the mean, x bar, x is just a number, and if you plug it in, all in there, what you get is just the standard simple expression of the Gaussian distribution for a single variable. Okay, now in case you haven't dealt with multivariate Gaussian distributions, it depends on your talent regarding statistics and so on. Some people see it right away, other people it takes it a little longer. So let me just try to give you a few minutes of intuitive feel by looking at the bivariate, right? The bivariate is the case where x is just x1 and x2, right? So imagine that you just had 2 frequencies. So if you had 2 frequencies, now it's kind of, I'm not going to try to do 3D, but what I can say is that if you have, let's say, the first frequency on this axis and the second frequency on this axis, right? The probability distribution axis would be coming perpendicular to the board going out. So there is an axis like this, right? The mean of x1 and x2, let's say, could be here, right? So that's the average vector. And what that means is that if this is a Gaussian distribution, you can imagine, and by the way, you might want to go to Google and look at bivariate Gaussian distributions because there are some nice graphs in there, nice plots. So here what we have is a bell, right? Some sort of a bell that has a peak at this mean here if it's Gaussian, and it's like that, right? Now, you can actually take a cut at any height. And if you take a cut at any height, you might see a figure, I don't know, it depends on the correlation and so on, but let's say you could see a plot like that, right? That means that the bell is kind of elongated this way and narrower that way. It's a bell like this, right? That slice gets smaller and smaller as we go up the bell, or bigger and bigger as we go down the bell towards the flat point, right? Okay. Now, let's see, where's my thing? All right. In the scalar case, the standard variable was x minus the mean divided by the standard deviation, right? In the multivariate case, the standard thing is parallel. X now is a vector, right? And that vector is the variance to the 1/2, which would be the standard deviation of all the variables, to the -1 multiplied times x minus x bar, right? So you can see here that all you do in the scalar case is divide by the standard deviation. Here the division, because it's multivariate, is just pre-multiplication by the square root of the variance, right? Which is the same thing. Now, the way we went from here to the chi-squared was, we said z was xs squared, right? Now, in the case of a vector, the way you square the vector is you multiply the transpose of the vector times itself, right? So if you have a vector ABC and you multiply it times its transport times its transposed, ABC, you get a squared plus b squared plus c squared, right? So what we do then is we take this vector here, standardize, and we square it. And so by squaring it, that is transposing it and multiplying it times itself, we get x minus x bar transpose. These are vectors. Then this was reversed. This matrix is symmetric, so nothing happens to it, except the order just got changed. And then multiply times itself, which is this multiplied times this. Right? And that becomes, this became the z, and this becomes, I'm sorry, this is, yeah, this became the z, and this is the z here, okay? Now this z here, it's a number, right? Because this is a vector times a matrix times a vector. So this is x minus x hat transpose. This multiplies to sigma, tau to the -1 times x minus x hat transpose. And so we see that the z variable of, if we standardize a multidimensional one, is the Mahalanobis distance. That is, if you want to write a PDF of the multivariate Gaussian, you could say that it is a constant alpha multiplied to e to the -0.5 times z, right? That z is the Mahalanobis distance. So that's clearly the role of the Mahalanobis distance, right? It just becomes the number here in the distribution of the not likelihood, but the probability density function of a vector x. Now, as you might expect from the scalar case, the variable z here, if it was in the scalar case, z was chi-squared, right? With 1 degree of freedom. In the multivariate case, z is still chi-squared with k degrees of freedom. And k is simply the size of the vector x, right? x1, x2, xk. Now, just like we have tables or MATLAB commands for the chi-squared with 1 degree of freedom, we also have something that tells us what is the CDF, the cumulative distribution function of the chi-squared with k degrees of freedom. So if I want to know what is the z critical for a system that has for a situation where I have k frequencies, then all I have to do is to say chi squared inverse. What do I want to do? I want to have 1 minus my desired type 1 error. But then instead of writing 1 here, I write k. And so that gives me the critical value of the chi-squared distribution with k degrees of freedom, such that the probability that the z is bigger than this, so that z has 1 minus type 1 probability of being smaller than sz. Therefore, our test is get the vector, right? Compute the Mahalanobis, which is z, as x minus the mean. Where do we get this mean? This mean, we got it because we've already looked at a bunch of data before, and we know what is the mean, and we know what is the covariance matrix, right? And so we calculate the z, which is the Mahalanobis, and then we have our zz, it didn't depend on the data, and if z is greater than zz, we announce damage. Okay, that's it. So this is the extension to the multivariate case of the criteria to identify damage by deciding that the vector that you have obtained is very unlikely if the damage was coming from that distribution. I mean, if the data was coming from the healthy distribution. Now, this is it. I don't have anything new that I want to add, but I want to summarize, again, for those that are less familiar. I can't see the fault of repeating myself a couple of times. So, I know this thing can sound rather abstract at first. So here it goes. From the perspective of an actual application. So I have my structure here, right? And so I perform system identification, and let's say that I'm able to find 3 frequencies. And so my 3 frequencies are these 3 numbers here. 3 frequencies, right? I did my ID. Typically, I would do this without knowing the loads, So it would be done from the stochastic system identification scheme that you learned just recently. So now I have those three frequencies, and that was on Monday, and so I do it on Tuesday, on Wednesday, on Thursday, twice on Friday, etc., 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 right? And after a while of getting these three frequencies, we stop. And we say, okay, that is my reference, right? That is my reference. I'm going to assume that my reference is a set of data that if I had more and more and more and more, eventually I would be convinced, if my system doesn't get damaged, that it's kind of Gaussian, multivariate Gaussian, because it's not just one thing, right? It's three things. So I say, okay, from here we calculate the mean. What is the mean? Well, just the average, the mean of that line, the mean of this line, the mean of this line, right? And we calculate the covariance function. How do I calculate the covariance function? Well, let's say that this vector is v1, and this vector is v2, and this vector is v3, and so on, right? And this is the mean. So to calculate this, I would say something like this: v1 minus the mean, right? That's a vector like that, times v1 minus the mean transpose, plus v2 minus the mean times v2 minus the mean transpose, plus v3 plus v4 plus v5 plus v6 plus, let's say this is vl. So plus vl minus the mean times vl minus the mean transpose, right? So I add all of them, and then whatever I get, I divide it by L, right? So the average of that product is the covariance. Of course, in order for that to be reasonable, I need lots of them, right? I can't just do 5 or 10. I need enough of this stuff so I can get a reasonably accurate value of the covariance matrix and of the mean. So now I have my covariance and my mean of the reference state. Now time passes, right? Time passes. And we're now in the future someday here, and we want to detect whether our structure is damaged or not. So basically the question we want to ask is whether, if we measure the frequencies, so we measure the frequencies and we get A1, A2, and A3. So those are the frequencies the day that we are testing to check for damage. So we get these three frequencies. Our question is, are these three frequencies logical for that model or not? Do they look like they could be reasonably coming from this model or not? Then we do as follows. We say, okay, given this data, its z value, which is its Mahalanobis, it's equal to A1, A2, A3 minus the mean, right? X bar from here. Transpose, that's a vector horizontal, times the inverse of the covariance that we've calculated times the vector A1, A2, A3 minus the mean, and we get some number Z, right? Some number, it's a number. So we get that number Z. Then we compute our Z critical depending on what kind of type 1 error we are willing to tolerate. So we say we are happy with 5% type 1 error. And so we say chi 2 inverse of 0.95, right? which is 1 minus the type 1. And how many degrees of freedom? 3. So we run that command and we find Z critical. Then we compare Z critical and we say, if Z is less than Z critical, no problem. Or at least we do not announce damage. If Z is greater than Z critical, we announce damage. That is, in a nutshell, the procedure for outlier detection when the data that you accumulate can be assumed to be multivariate Gaussian. In practice, sometimes adjustments are made for this and that, but this is the essence of the approach, and when we look at some numerical examples, you'll get a better feel for it. I am going to try to prepare some sort of homework where you can test your understanding of it. All right? Okay.